Welcome to the instrumental analysis lecture. Because of the closure of the university, we have to find alternate methods by which we can communicate with you and get the information over to you. So I'm making a series of videos, and they're going to be posted on Blackboard, and I will give the lecture just as if I'm in class, and then you can email me questions or text me or phone me questions, and we communicate like this. So I'm starting at the beginning of atomic spectroscopy. And if you remember, molecular spectroscopy was the experiment we did with cobalt and chromium, where we had these large absorption bands, right? The bandwidths of the absorption bands were large, maybe 40 nanometers wide, okay? Remember, the effective bandwidth is the bandwidth at half peak height, okay? So we had relatively large bandwidths, and that drove the type of instrumentation that we had. Remember, we had a broadband source, we had a wavelength selector, then we went to the sample, then we had the detector, and then we had electronics, right? But if we look at molecular at atomic spectroscopy and not molecular spectroscopy, what we see is that atomic bands are due to specific transitions. So if we look from here, from the 3s to the 3p, we see that, for sodium, that's the energy associated with that transition, right? The energy here is in electron volts, and it's a specific amount. As a result, atomic bandwidths are very narrow, all right? In a fraction of really small, fraction of nanometers, okay? And therefore, we need a different design of the instrument, because Bayes' law requires that the bandwidth of the source must be narrower than the absorption bandwidth. And that was easy to achieve in molecular spectroscopy. So the bandwidth was 40 nanometers, the effective bandwidth. So as long as the wavelength selector can give us less than 40 nanometers, let's say 10 nanometers, it was fine. But with these narrow bandwidths, we have to change how we get the source to be narrower than the bandwidth of the transition here. All right, and that's what drives all of the instrumentation. Okay. This is just a reminder of Gen Chem, where we have a singlet state, a singlet excited state, and a triplet state. You notice the difference? Spins are paired here, spins are paired here, spins are not paired there. All right? We'll talk about this later on, because this is the Doppler effect, which we talked about, which is really interesting. And it talks about the fact that the act of measuring something changes the value of what is being measured. That should be interesting to you, but the last time it was. Okay. So let's start talking now on this level, right? So that in atomic spectroscopy, we have the analyte here, right? The analyte is in solution, and the first thing we have to do in atomic spectroscopy is what? The name is atomic, so we have to convert them into atoms. All right? So atomic spectroscopy has this process. We take the sample, and we call it nebulization, or we create a spray. All right? Remember, in here we have the metal, but the metal is kind of solvated, so it's in this capsule. It's surrounded by these water molecules, and we get this spray, and that's similar to what you do with your hairspray or any kind of nebulizer. Then we have desolvation, in which we strip the solution away, all right, and we get this solid gas aerosol, all right. And then from here, we have a number of processes which lead to different outcomes, right? We have volatilization, we get these gaseous molecules, all right? And from gaseous molecules, we can do some kind of excited molecules here, but we're looking at molecules, right? We can go to atoms, and we can do some spectroscopy here, that's atomic spectroscopy. Or we can go to atomic ions here, and we get ionic. We get some kind of ionic system, right? So we're not interested in, we don't want these other processes to occur, actually. We want atomic spectroscopy. So if you keep this in mind, then everything else that we do afterwards is kind of driven by that. We come to these later on. So here we look at the source in atomic spectroscopy, right? The source is a hollow cathode lamp. That's the most common source you would see. And what we have in the hollow cathode lamp is we have a glass shield here, all right? Around, we have this here. This is evacuated. We have an anode here. We have a cylindrical cathode. And on the cathode, we deposit the metal of interest. So if you're looking at magnesium, we have a layer of magnesium in here. Right? And then this is connected to the instrument. And this gives us a narrow out. The bandwidth of the output here is very narrow. All right? So what happens is we apply a potential across the anode and the cathode. All right? We vaporize the system. All right? So we have in here, we create what is called an atomic cloud. All right? And in this atomic cloud, all right, we have enough energy to excite molecules from the ground state to the excited state. Right? And when they get to the excited state, they return to the ground state. And then they release radiation, and the radiation goes across here. Now notice it's cylindrical, and it's cylindrical for a reason. That means it focuses all of the radiation that's produced out in that direction. So we get a narrow, the radiation has a narrow line. It's a very narrow line. Right? And that's why we cannot use in molecular spectroscopy, we use a monochromator, right, to select a narrow band of radiation. But a monochromator does not give us a narrow enough bandwidth. So we have to actually use the metal of interest. Right? So one of the disadvantages or hindrances to atomic spectroscopy is that we have to have a hollow cathode lamp which is metal specific. Right? So if we're doing calcium, we have to put in a calcium lamp. If we're doing zinc, we have to put in a zinc lamp. They've now created some lamps which have multi-elements. So we have a calcium, magnesium, zinc lamp. Right? So that does those three. Right? So that you have to keep in mind. All right? We have another type of source. I mean, in all of these, if we go back, all we're doing is providing energy to excite the molecules from the ground state to the excited state, right? Here we're doing it by applying a potential between the cathode and the anode. Here, all we're doing is the same thing, all right? We have a lamp here, we have a ceramic holder, we have the metal in there, but we're applying a radio frequency to the system here, that's the lamp, right? And we apply the radio frequency. And we do the same thing. We excite the molecules from the ground state to the excited state, and the radiation that's produced has a very narrow effective bandwidth, right? So the metal of interest is in here, is in this lamp, but instead of having electrical potential to excite it, we use a radio frequency. All right. We'll talk a little bit now about instrumentation. You've seen some of this instrumentation before. This is an old-time instrument. This Ebert monochromator doesn't exist anymore. You won't find it on many modern instruments, but it's used a lot for if you want an instrument that's portable, that you can take into the field to make a measurement, because it has very few moving parts and it's kind of rugged. But just look at it. It has a power supply, right? And it's connected to the hollow cathode lamp. We're using a flame here, so your analyte is in the flame, right? And then radiation goes through the flame, and it bounces off this this mirror here to the grating, all right? Then we get resolution here, and then we get some kind of output, all right? This is your detector, and the detector in most cases could be something like just a normal detector that you've used in molecular spectroscopy, right? And then we have an amplifier, and then we have readout. So that's the simplest system that we can talk about, right? So that this can be something like a photo tube, And remember, a phototube or the output is, it's strong enough that you don't need a photomultiplier tube. This is more likely the kind of instrument design that you would see in a more modern instrument, right? So we have a lamp, and then we have a chopper here, then we have the flame, all right? Then radiation goes from the lamp to the flame, and then we have a Cherney-Turner monochromator, right? Then it goes to the photomultiplier tube here, then a lock-in amplifier and some kind of reader. Now, if you look at it, the most visible difference that you see is the type of monochromator, right? This gives you better resolution than the Ebert monochromator. But then there's something else. The instrument has a little more sophistication than here. And if you notice, what we have here is the lamp, right? Then we have a chopper here, all right? So some radiation, this is what the chopper looks like. The chopper is just like a pizza that you eat alternate slices, right? So this is solid, this is open. So when you have this chopper, what happens is, at one instant, light passes through here, comes out from the lamp, it goes up here, okay, to this mirror, it bounces off this mirror, comes down here, goes to the monochromator, and it goes to the detector, right? It goes to the phototube and then reader. Then sometimes what happens is, if the source from the lamp gets this open slot here, then it goes straight through the flame, right? Bypasses this system here, goes to the flame, then it goes to the monochromator, then it goes to the photo multiplier tube, and then to the lock-in amplifier. So this is a lot more complicated than this one. And it does two things that we don't do here. The first thing is that here, at some point in time, the signal from the lamp bypasses this flame. The flame has a sampling, right? And it bypasses the flame, and it goes straight to the photomultiplier tube and then to the reader. What this does is to give you this allows you to be continuously subtracting the background, right? Because what's happening is you're just measuring the intensity of the lamp, and that compensates for fluctuations in the lamp intensity. Because if we have fluctuations in the lamp intensity, then we're going to have fluctuations in the readings that we get, because the absorbance values will be constantly changing simply because the intensity of the lamp changes. Then it goes through the flame. Part two is it goes through the flame. All right. Now, if you remember your molecular spectroscopy, right? In molecular spectroscopy, we get a constant output, right? But here, the output isn't constant, right? Because we have a chopper. So that the chopper is putting some frequency dependence on the output. So the output from the flame actually looks like that, right? It has some kind of periodicity to it, right? And this allows us to do something as well, right? If you look at the flame, right? With the flame, you can actually see radiation. When the flame is on, it's orange, it's blue, it's something, right? So that's radiation. And once there's radiation here, right, in the flame, that radiation goes to the monochromator, and then it goes to the amplifier, to the photomultiplier tube. The monochromator is set at a particular wavelength, so it discriminates against all other wavelengths. But we might still have the wavelength of the lamp. All right? We might be getting the same wavelength from the lamp as we're getting from the flame. All right? So that we have to figure out some way to distinguish the two. And by putting a frequency dependence on the flame, on the output from the source, which is here, all right? What we're doing is allowing for the instrument to actually what is called lock into this frequency and only measure this frequency. Because the output from the flame is continuous, right? The output from the flame is going to look like this, right? It's going to be continuous, but then the output from the sample is going to have this periodicity to it, all right? So that what happens is the lock-in amplifier, you see here, it locks into the frequency of the chopper, and it only amplifies the output that has the same periodicity as the periodicity that we get from the chopper, right? So that's one other feature of the more modern instruments, right? It allows for putting a frequency on the source. All right, that's just what we had before, and that's just a bigger version in case you didn't see it before, right? So if you have to draw, if one question says to draw, the instrument, a common instrument for atomic spectroscopy, you draw something like this, right? So you must have a source. The most common source is really hollow cathode lamp. Then you show me this, then Trinity Turner, then you have a photomultiplier tube, and you go from there. All right? We can also have in this system, in some systems, we can have a reference source, right? So let's go back. Let's see if we can do that over there. So let's go back to here. We'll forget that for a while. All right. So some methods by which we can introduce the sample. We do sample introduction in atomic spectroscopy, right? We can do a pneumatic nebulization, and that's for solutions on a slurry. Ultrasonic nebulization for solution. Electrothermal can be for solid, liquid, or gas. Hydride generation, direct insertion, laser ablation, arc and spark, and blow discharge. So let's talk a little bit about it. Electrothermal, what we have would be the sample. Let's assume the sample is a solid, and we have two electrodes, right? And the electrodes will be connected to some kind of power supply, right? And then we'll apply a potential across it. And what will happen, it will heat up the sample and vaporize the sample. All right? So the sample would vaporize, and we have the beam from the source passing through it, and we get a reading, right? So for electrothermal, we can use solids, we can liquids, or some kind of a solution. Laser ablation is similar to this, it's just that we'll have the sample, and instead of having putting a potential across it, we have a laser that provides a sharp laser beam, an intense laser beam. Again, it vaporizes the sample, and we get a reading. We can use a glow discharge. We looked at electrothermal. We looked at laser. Pneumatic nebulization, which works with a solution or slurry. So we have to think about the outputs. If we look at, for the output, intensity as a function of time, all right? In the first system that we looked at, where we had sample just constantly be in the flame, where sample is constantly being fed into the flame, then what happens is, as a function of time, we start with no signal, and after a while the intensity of the signal increases, but then it remains constant, right? Because we're constantly feeding sample into the flame. When we look at most of these techniques, like when we look at like laser ablation, arc and spark, electrothermal, they're going to look differently, because what's going to happen is, if this is a function of time and sample intensity, you're going to have this, right? The signal is going to increase, then it's going to remain constant, and then it's going to decrease, right? Because remember what happened, we vaporize the sample, the vapor gets into the beam of light, and then after a while, there's just no more sample, it just disappears, right? So you have to keep in mind that these methods result in different types, the output would be different, right? The most common one is this, you get that kind of continuous. These are just examples of, this is the high pressure gas flow that's in there. This is actually what the instrument would look like. Not the whole instrument, but just this part of it here. So let's look again. So we have this narrow, this really small capillary here, and it's when your sample is in solution, right? And it goes into here. Here we have fuel coming in, and we have oxidant, right? And the sample is being aspirated in, all right? And what happens is we get these small sizes of little droplets, right, of the sample, because the sample is coming in here, comes in this form, right, droplets. So the first thing you have to remember is that these are going to have different sizes. I draw them all as if they have the same size, but they're different sizes, all right? And this is being aspirated into the flame, all right? And as it goes into the flame, all right, it gets excited, and we have the beam of light passing through the flame and going to the detector and everything else, right? The problem with ignoring this part in the middle here is that when we do the process of this nebulization, right, we create particles of different sizes, right? So that's what's happening here. We have these particles of different sizes here. Right? If we have particles of different sizes, then if they all get to the flame, right, the output is going to vary as a function of time, because as time goes by, there's no consistency in the amount of sample that's being aspirated into the flame, right? Because sometimes we have a lot of large particles, so we have more samples, sometimes we have only smaller ones. So these baffles here, all right, these here, all right, what they do is start with an input like this, where we have a wide range of density, large range of particle size, to bring it to all uniform size, all right? So that when the sample gets to the burner head, we have a uniform size here, right? And as a result, one of the disadvantages of this type of insertion is that most of your sample just goes down the tube, right? You just waste most of it, right? And it goes from here, all right? So when we start here, we have a wide range of sample size, right? When we get to this point here, the sample sizes are more or less uniform, all right? So think of it here as, at this point when we say it's uniform, it's like the cuvette, right? When you have the sample in the cuvette, the concentration of the analyte in there is constant. If you pull the cuvette up a little bit and take the measurement, it's the same. Here, the measurement won't be uniform, but here we have a uniform sample of those things. So that brings us back. This is used in electrothermal, right? You put the sample in here, you apply a potential across it. This is, you're applying this is the one where we apply a potential, right? So we apply a potential here, we have negative here and positive, and we apply a potential right across there, okay? And then the sample is instantly vaporized. We have some air coming in here, and the sample is up here, and we have the light, beam of light across there. Again, notice that in this case, your output is going to, if you take a function of time and intensity of the output, right? It's going to be like this and like that, right? And it might not be even as straight as this because, dependent upon the time and how many particles just actually get into the beam of light, all right? It's not going to remain constant because as soon as you turn this potential off, it's going to return back to here, and it might be a little more wobbly than what I drove it. Right? So far so good. Let's go to some notes that we have in Microsoft Word.